divided by p1 of y given x dy dx, right? This is what I am interested in computing. I could remove p0 of x and p1 of x are both uniform. This is uniform in 0 and 1, and this is the same as p1. P0, only the conditionals are different, right? The distribution on x is always uniform between 0 and 1 here. So this is 1. I can remove this. So I can write this as the integral from 0 to 1 relative entropy between P0 of y given x, P1 of y given x, dx. All of this simplifies nicely because this is 1. So now I have the integral of P0 y given x log P0 of y given x by P1 of y given x dy. That is the relative entropy between P0 and P1 for y given x. This is Gaussian with mean m0 of x and variance 1. This is Gaussian with mean m1 of x and variance 1. So we have a closed form formula for this. Okay, we saw that before. So this is the integral from 0 to 1. Turns out that this relative entropy is nothing but just m1 square of x. Let me write it down explicitly. M1 of x minus m0 of x square, the difference between the means, divided by 2 sigma square. Sigma is the variance, which is 1 dx. So this is now the integral from 0 to epsilon of m1 of x minus m0 of x square by 2 dx, because m1 is this function, right? Look at x, this is m1 of x. We only need to integrate from 0 to epsilon. The rest is our algebra. I will let you do the calculations. So this is L square epsilon cubed by 6. If you work out, you take this function, square it, and work out the integral, you get L square epsilon cubed by 6. So this is the relative entropy, and this has to be 1 over n. And so this means that epsilon is 6 over n L square raised to 1/3. So this tells me what is the right epsilon to select in the Lee-Camp's bound. If I made epsilon too large, then my relative entropy will be larger than 1 over n. And if I make epsilon too small, it will be smaller than 1 over n. But this scaling gives me the epsilon that makes the relative entropy to be 1 over n. Now, once we have that, delta is L epsilon. So you can see that this is going to be just something like some constant k. We can absorb L in the constant, it doesn't matter, times n to the 1/3. So here k is the constant that I care about. This is L times 6 over L square raised to 1/3. Some constant. This is what k is. And so what we can now say is that the minimax risk is greater than delta over 8 e to the minus 1. So this is like k double prime, some other constant times 1 n to the minus 1/3. So this is the scaling I get. That the minimax risk scales as a number of samples raised to minus 1/3. That is ultimately the quantity of interest in these paths. Turns out that this is optimal, meaning there is a method that can achieve this, but we won't go through it. It's a little bit of a tedious calculation, the achievability part, but this is the scaling. So we'll stop the Lee-Camps method here, and we will move to the second method that is also widely used, that is the Pharos lower bound. Any questions, by the way, about this problem?
Is there any intuition as to why this problem has such a worse scaling law as compared to the previous?
I mean, in the sense that you're still estimating these full functions, right? M0, M1, although it's at one point, what you get are samples that can be anywhere between 0 to 1. So it won't be as efficient. You only care about the value at 0, but x is anywhere between 0 and 1. So this turns out to be the right. Basically, you can generalize this to be dependent on the dimension of the problem. This is scalar. There are bounds that you can do similar calculations if you are in D dimension. And then I think you get a scaling like n to the 1 over 2 plus D. So the higher the dimension you are, it will really hurt you as well. So all these bounds can be done. Very similar things, but in D, if x was in, say, Rd, I believe you get something like n to the minus 1 over 2 plus D. Or, yeah, something along these lines. So the dimensions hurt you a lot, and also the fact that now you have a whole function that is unknown will affect the scaling.
So was this just a story example, or does this have any implication with respect to some setting?
So this is just a problem where, you mean what's the application?
I mean, this particular example, does it come naturally from something, or this was just a story example?
Yeah, so ideally you want to estimate M0 and M1, the functions that are unknown, right? You have n examples, right? X is a uniform between 0 and 1, and y given x.
Yeah, but specifically at 0 point are we estimating?
Here we are estimating at 0, but you may want to estimate the full function, right? And so it's a problem of basically the regression. Given y, you want to estimate what the mean value is. So you're observing some output y, right? Or you're observing x actually, and you want to estimate what the label is, y. So the mean is mx, and there is some noise added to it. So here, so that is really the setting. It's like regression, where you're given one query point and you want to estimate the label, right? Now this m is not a linear function. It can be an arbitrary function, but it satisfies a Lipschitz constraint, meaning it doesn't change very quickly. That is the setting. So if you estimate mx, then you given a query point x, you can estimate the average value of the label, right? So that is, in this case, it so happens, just to simplify, we are saying my query point is 0, and I just want to estimate sort of the difference at point 0. So that is sort of, so this is an example, if you like, of regression. Okay, so what's the Fano lower bound? So it's a generalization of the Lee-Camps method, where you select n distributions in the set P. So in the Lee-Camps method, we had 2 distributions. In the Fano, we have now a more powerful option. Instead of 2 distributions, we select n distributions. What you do is now, just like you have the delta parameter, you have an alpha parameter in the Fano lower bound. So you look at the pairwise distance between each pair of distributions at the parameter of interest. That's alpha, and you look at the worst case. And then beta is the maximum over j not equal to k, d of pj and pk. So you look at the worst case relative entropy. The largest relative entropy you get, or the Kullback-Leibler divergence, what you want to call it, between the pair of distributions where j is not equal to k. And the Fano lower bound says that the minimax risk is bounded by alpha over 2, 1 minus n beta plus log 2. Now, over log n. This is the Fano's lower bound. So alpha here again is the closest distance between the distributions at theta. So you want to choose the distributions for which alpha is large. So it's a term here. But if you choose the distributions to be too far apart, then beta becomes large. It's the pairwise relative entropy, and in fact you look at the worst case. So you look at the two distributions that are as far apart as possible, and that is what determines beta. Alpha is determined by two distributions for which theta is as close apart as possible. So you want to keep the thetas far apart for the closest pair of distributions, but you want to keep beta as small as possible for the worst pair of distributions. You have to really be judicious in how these distributions are chosen, because you get hit twice. Right? If you make like the worst case distributions far apart, you get penalized by this beta term here. You have 1 minus beta, right? And conversely, if you make the distributions too close, then alpha will be reduced. So again, there is the same tension between selecting alpha and beta. And more general, what we often do is, the usual choice is to select n beta to be less than log n by 4 or something. You want this quantity to be less than n. N is the number of distributions you have. And beta should be like log n by 4. And then I think if n is greater than 4 or some small constant, Rn of p will be greater than alpha by 4. So your scaling law is determined by alpha, but beta determines, like, you have to first set beta to follow this rule. Once you select beta to be of that form, it will tell us what alpha is, and the minimax risk is lower bounded by alpha by 4. So this is how Fano's lower bound is applied in this setting. So the name Fano might be familiar to people who have taken information theory. It's basically the same technique that is used in information theory. So when you have to prove channel coding capacity, I don't know, virtually every problem in information theory, multi-user information theory, when you prove the converse, it starts with Pharos Lemma, right? That is how virtually every converse starts off. So it applies here as well. So we'll start with Pharos Lemma. So let y be a random variable that is uniform over the set 1 to capital N let P1 to Pn be distributions such that probability that x equals x given y equals j is Pj of x. So we have a distribution. So x is basically the distribution or the observed random variable. Y decides which distribution was used in sampling x. We let y hat equals gx be an estimate of x. So y hat belongs to the set 1 to capital N. Okay? So given x, you want to decide which distribution was selected in sampling x. And gx is our estimator, some function. We had psi before, now because this is not binary, we'll call it g. Then if you consider the following quantity, this is the probability that y is not equal to y hat. This is the probability of error. Right? So if J was the true distribution, under Pj, y hat is not set to be J. And you average over all J from 1 to n. This is the average error probability. Okay, this is the same as probability that y is not equal to y hat. Because y can take values 1, 2, 3 up to capital N. And y is uniform on this set. So you can condition on y equals J to basically get this thing. Okay? This quantity is the probability of error in the following setting. I'm selecting y to be 1 to n at uniformly at random. Once I select y to be j, I'm sampling x from this distribution. Then I'm using g to be my estimator for y hat, and I'm seeing whether y hat equals y or not. So this error cannot be too small. We want a lower bound on the error probability. So we want to say regardless of how g is selected, there is going to be an inherent limitation, a fundamental lower bound on this error probability, and this is greater than 1 minus I of xy, the mutual information between xy, plus some small constants divided by log of n, the number of points.
I think you wrote be an estimate of x. You meant
Be an estimate of y. Right? So this is a lower bound, does not depend on g. It just depends on the joint distribution between x and y. Okay, and then log n is the entropy of y. And then there are some constants which can be tweaked. These are not important. They can, depending on the problem, this can be made smaller, larger, and so on. So, but this is the main thing it is saying is that the mutual information between x and y is large. Then you are going to subtract a larger quantity here, which means that your error probability will have a smaller lower bound. You can do better. If the mutual information is 0, then there is nothing you can really do. You have to do a random guess. Your error probability will be like 1 minus 1 over n if you have n options, and this is saying it's 1 minus 1 over log n, basically. So it's a bit weaker than that, but that's not the case where we are usually interested in. This works for any distribution x comma y, any joint distribution between x and y, this works. And this is the bound that we can use to lower bound our minimax risk. So this is the bound if you have a background in communications and have taken information theory course. If you're lucky, you may have taken a multi-user information theory course, and you will see this bound used over and over for proving capacity theorems for all communication channels, like point-to-point channels, all kinds of multi-access channels, broadcast channels, relay channels. This is the bread and butter for people who work in information theory. And the good news is it also applies in this setting. So we won't prove it. The proof is because it is not really related to machine learning. The proof is in Cover and Thomas. I think people who have a background, this is a textbook, chapter 2. People who have a background will sort of get bored, and people who don't have a background can just read the proof. It won't give much additional insights, so you can just check the textbook. So how do we use this bound to go to the new setting? So what we will do is we'll prove a slightly rewrite this in a slightly different way. We will rewrite Fano using the beta term, using beta. So we'll replace the mutual information with the relative entropy. Okay. Just want to rewrite it. So note that I of xy, the mutual information, is the relative entropy between x given y equals j and px, and you take the expectation with respect to y. This is how relative entropy is defined, or how we get mutual information from relative entropy. Okay, we saw these formulas before the break. You should know all these things when you do these manipulations. Now, px is just the average distribution I can write px in this form. We take the sum of y equals j from j going from 1 to n and take the conditional and average it, just marginalizing px from the joint distribution. So I have I of xy. First, if I take the expectation with respect to y, it's this quantity. I'm going to put I here. This is just breaking out this expectation. The expectation over y is 1 over n, summation of I going from 1 to n, d of p x given y equals psi and px. This is 1 over n, summation of I going from 1 to n. X given y equals psi. And then I have the second relative entropy term. So px itself is a mixture of these distributions. Now the point is that the relative entropy is known to be convex in the second argument. In fact, it's convex in both the arguments. So what I can do is I can bring it out like this. If I bring out the summation, then I have this. Over n square. So this is 1 over n times summation of I going from 1 to n of the relative entropy between these two. But if I were to bring this summation outside, I will get an upper bound because the relative entropy is convex in both the arguments. It's also convex in this argument. So we can use Jensen's rule here. Okay. And now each of these terms is less than beta. So the whole quantity is going to be less than beta. Because beta is defined as the maximum between the relative entropies between Pi and Pj. And so the point of all this exercise is that this mutual information can be replaced by beta and you also get a lower bound. So the Pharos lower bound is this. Probability that y is not equal to y hat is lower bounded by 1 minus n beta plus log 2 by log n. Okay, so this is still the classical lemma that we have, right? We want to use this to establish the minimax lower bound. We want to take this Pharos lemma which is about the probability of error. So this is, remember, just 1 over n summation of I going from 1 to n pi y hat of not equal to I. We want to, this is the standard Pharos lower bound. The only change I did was I replaced the mutual information term by the beta term, which is larger than the mutual information based on this calculation. Okay? And as a result, now we want to use this lower bound to establish the minimax lower bound. So that's a separate part. That's new. I don't think anyone would have seen that before in the information theory course. So this you might have seen before, these calculations. So we will again use the same sort of arguments as in Lee-Camp's method. So what we will do is define, so we are given an estimator. So we are given theta hat and the distance function d of theta hat and theta. Right? What we do is we define a detection problem or a decision rule y hat to be arg min d of theta hat and theta j. So we choose the parameter that is closest to our estimator among theta 1, theta 2 up to theta n. So when we pick this n prop points p1, p2, pn, we have the associated thetas, theta 1 to theta n, and we pick that distribution that will be closest to the estimated parameter and set that to be y hat. Okay? So this is the same as we did in Lee-Camp. Then what we can show is that expected value over pj of d of theta hat and theta j this quantity is greater than alpha by 2 times the probability that y hat is not equal to j. This is what we will show. The proof is virtually the same as in the Lee-Camp's method. So the left hand side is expected value over pj of d of theta hat and theta j times the indicator function that y hat is not equal to j. Left hand side is greater than this because we are adding just the indicator function here, which is less than or equal to 1, and then following the same set of steps. Since alpha is the minimum distance, you can show that this is greater than alpha by 2, pj y hat is not equal to j. We'll leave this as an exercise. Okay, so then once you have that, the rest of the argument is a direct application of Pharos lower bound, the classical lower bound. This is EP d of theta hat and theta p. Okay, this I can write it as inf theta hat max j in 1 to capital N EPJ d of theta hat and theta j, because what I did was I replaced the supremum over all p with the max over p1 to pn, and that's only going to reduce the value. Now this quantity, the one I have, if we use the argument we just made, this is greater than alpha by 2 if theta hat max j in 1 to n pj that y hat is not equal to j. So if we just substitute for this, then expected value of pj d theta hat theta j is greater than alpha by 2 pj y hat is not equal to j. Okay. This is greater than the average of j going from 1 to n pj y hat is not equal to j. The max is lower bounded by the average. This is exactly where we can apply the Pharos lower bound. Okay. We are looking at, so for any choice of theta hat, Pharos lower bound, so this is in P, the probability that y hat is not equal to y, and this is exactly where Pharos lower bound can be applied, the one we had nicely written up here. So this is greater than alpha by 2, 1 minus n beta plus log 2 by log n. So this is the Pharos lower bound that is widely used in this minimax literature. So we'll finish off by doing an example that illustrates how Pharos lower bound can be applied. We'll go back to the same problem we had before to break, but now we'll consider a lower bound for the full function, the regression function, not just the value at 0. So, any questions before we start? This is the derivation, the full derivation. So all these problems, basically the way this minimax literature works is you have to be judicious in selecting these distributions P1 to Pn. Okay? They have to be, once you select them, you can compute alpha and beta. Beta is the pairwise relative entropy for the largest worst case distance, and alpha is the pairwise distance in the best case, the smallest distance. And so you get hit twice. So you have to somehow carefully select these things, compute these quantities in the right way, and that gives you the minimax lower bound. So discretization is very important in this literature, selecting the right subset of like distributions like this. And this is how the whole literature has evolved till date. So we'll do an example. Again, it's the same setting. We have x1, y1 up to xn, yn, which is sample IID, pxy. P of x is the uniform between 0, 1. P of y given x is Gaussian with mean mx and variance 1. Same setting as before. And mx is Lipschitz. So what that means again is my minus mx is less than L times y minus x. Okay. So what we will do next is we have to now select m0 of x, m1 of x up to m capital N of x, or actually just make it m1 of x, m2 of x up to m capital. These are the functions we have to select. Px is uniform between 0 and 1, so the only freedom we have is in choosing the m here. And in the Lecam's case, we had M0 and M1. We selected two of them. Here we have to select n of them and evaluate the Pharos lower bound. Now what we will do here is we will choose our functions to be like decision bumps. So in other words, we will take our interval from 0 to 1. We will divide it into t intervals, into t disjoint intervals. 0, 1, 2 up to each is of size 1 by h. So we have the interval 0 to 1 and we simply divide it into t disjoint intervals like this, each of size 1, each of size h, not 1 by h. So t is 1 by h if you like. What we do in each interval is we put a small bump. So here we may, so one choice of m would be like this. We may put a bump here, we may put a bump here, and so on. The slope here is at most L, so this height here can be LH by 2 at most. So we'll put a bump like this. This height is LH by 2, goes from 0 to h. This, if you put, here we are not putting that function. So here there is no bump. Here we decide to put. So we will have all such variations. We may have the all zero function as one option. We may put like a triangle everywhere as another option. In certain intervals we'll put the triangles and in other intervals we won't put the triangles. Right? That will be the idea. So what we will do is we'll have a whole family of functions that are basically designed by our decision of whether to put a triangle or not in each of the small intervals. Okay, so for that we will define a function phi x, which is defined like this. So phi x is 0 if x is less than 0 and x is greater than h, and inside it is a triangle. So this function here is actually phi x. So it is L h by 2 minus L by 2x if 0 less than x less than h by 2, and L times h minus x if h over 2 less than x less than h. So from 0 to h over 2 it's increasing. No, this is not right. Write this properly. I guess it is just Lx from 0 less than x less than h over 2. So we get this triangle, and then it is decreasing. L times h minus x. Okay. Now what we will do is we will define a shift of this. So this is one triangle, but we have to consider all shifts of them, right? So I will just define phi j of x to be phi of x minus j minus 1h. So the screen. Does anybody know how to get the screensaver off? Let me know, because I have tried a few things I could never get off on this machine. So okay, so phi j of h will be a triangle in this interval between j minus 1 and j. This is phi j of x. So phi 1 of x is a triangle here, phi 2 of x is a triangle here, and so on. We just define a shift. And now, instead of writing what we will do is we'll let omega to be a vector of omega 0, omega 1, omega 2, up to omega t. Maybe I'll just start at 1. I don't want the 0 index. So this is a t-dimensional vector where each omega j is either a 0 or a 1. So omega is just a binary vector, and m sub omega of x is going to be the sum of j going from 1 to t omega j phi j of x. So my function m omega is going to look like this. What that essentially means is that between the interval 0, 1, 2 up to t, I have omega 1 here, omega 2 here, omega 3 here, and so on. This is omega t. If omega 1 is 1, then I will have the triangle here, a small triangle. Omega 2 is 1, I will have a triangle here. Omega 3 is 0, I will not have a triangle. If omega t is 1, then I will have a triangle. So omega tells me what triangles I have in this particular expansion. For given omega, I have constructed my candidate function like this. So this will be the set of candidate functions that I select in computing the Fano lower bound. So how many different functions can I have? What will n be in this particular construction? What is the maximum value? How many different functions can I have in total? Each point can be 0 or 1. So there are a total of 2 to the t different vectors. So the maximum number of functions I can have is 2 to the t. Right? So if I have all 0, that is 1. If I have 1 and 0, that's another 1. 1, 1, 0, that's another 1, and so on. So I have 2 to the t different functions. Turns out that this will not be the right number. We will actually use something from coding theory to construct these functions to prune out the sets and then get a better lower bound rather than using all the functions. But in principle, you have all 2 to the t different functions that you can generate here. But we'll see reasons why that is not the right. You should not use all omegas. You should use a subset of them. Okay. So I have described what my candidate functions are, right? Okay. Now we want to apply the Fano's lower bound. So I know that my minimax risk is given by the inf over m hat. M hat is what I am estimating. This is my theta hat now with the candidate output function. Now instead of the soup over all m, I have to take the soup over all omega or the max over omega because my candidate functions are parameterized by this omega vector. I'll take the max over omega, expected value of p of d of m omega of x and m hat of x. This is what I want to compute. So note that this is the inf over m hat, max over omega, the expected value. The distance is now the squared distance. We select the squared distance. Actually, I take the square root of the squared distance. Doesn't really matter which one you select. Okay. And then I'm going to take the square root inside. Doesn't matter which distance, it's like proper Euclidean norms. We take the square root of the distance. So this is what we want to compute. So this is basically going to be the regression, the estimated regression. Okay. So now we know from Fano's law. So this is the problem setup, right? Once I've selected the functions. So Fano's lower bound says that this quantity, the minimax risk, I cannot really evaluate the inf over n hat in general, but Fano's theorem gives me a lower bound on this quantity. This is greater than alpha by 2, 1 minus n beta plus log 2 by log n. This is Fano's, this is a theorem. So once I have selected my functions, I can evaluate this. Here alpha is the minimum over all omega and say v of the distance. So the distance between m omega of x minus mv of x square dx raised to 1/2. This is alpha. You have to look at the pairwise distance. So let's call this just d square of m omega and mv. Okay, so it's a pairwise distance. For each omega and v that I select, I can compute I get the corresponding m omega and mv. I take the difference, square it, and integrate over all values of x. And beta is the max over omega and v of the relative entropy between the joint distribution induced by omega and the joint distribution induced by v. So remember, this is still going to be px, which is uniform, times the Gaussian with mean m omega of x and 1, and this is again px, which is uniform, the same, and mv of x and 1. So this is what, so I have to, now I have in this principle specified everything to compute the lower bound. I'm giving you omega and v, so I'm saying all my functions, candidate functions, are parameterized by this omega and v vectors, which are binary vectors, zeros and ones. They define what m omega and mv are. Using that, I can compute the pairwise distance and select the smallest one. And I can look at the pairwise relative entropy and select the largest one. Once I have that, I substitute it in here and I get my lower bound. There is one problem though, that if omega and v are arbitrary vectors, this distance will be very small. So for example, m omega could be the all zero function, mv could just be one small triangle and everything else is zero. And their distance will be very small, right? And that won't give you the right minimax risk. So you have to actually not use all possible choices of omega and v, but you will select a subset of them so that the distance is good. So let's look at these quantities more closely. So this is the distance, the integral from 0 to 1, m omega of x minus mv of x square dx. But note that m omega is a function that looks like this. You might have a triangle if omega 1 is 1. You may have a 0 if omega 2 is 0, a triangle if omega 3 is 1, and so on. mv of x is similar as well. If v1 is 1, you have a triangle. If v2 is 1, you have a triangle. If v3 is 0, you have a triangle, and so on. This goes from 0 to 1. This goes from 0 to 1. So taking the pairwise difference between them, okay, when you take this integral for each x in this direction, you're taking the difference between them, squaring it, and integrating it up. Now, in any interval where omega equals v, omega I equals vi, the difference is going to be 0 because they're exactly the same triangles. When omega is not equal to v in any given interval, you will see that the difference is basically one triangle square. So this can be simplified as the summation over all possible intervals over all possible integrals of m omega of x minus mv of x square dx, where x is from jh, or actually I should write j minus 1h to x equals jh. It's the same thing, I'm breaking it out across the different intervals. The point is that this quantity is going to be phi jx square times the indicator function that omega j is not equal to Vj. Omega j equals Vj, this difference is going to be 0. If it is not, one of them is 0, the other is not, so it will be phi j squared, where phi j is the shifted triangle. And if you simplify all of this will be the summation, because this is a constant, phi j of x squared in this integral is just like integrating phi square of x. The whole thing here will be summation of j going from 1 to t, the indicator function that wj is not equal to vj, times the integral from 0 to h phi square of x dx. This is what it will come down to. Because each of this in this interval is a constant. It's just the integral of phi square of x from 0 to, right? 0 to h. So this part here will be just the integral from 0 to h. So when they are not the same, it's like integrating phi square of x. You are integrating this triangle. So phi square of x is this triangle from 0 to h, which we define of height LH by 2. Okay, and so when they are not the same, it's like integrating phi square of x in that interval. When they are the same, it is 0. That's why we can take this summation of omega j not equal to Vj and then integrate phi square of x. So again, this is algebra, so I'll let you fill out the details. But what we are doing is we are taking the difference. If they are same, then the difference is 0, which is captured by this. If they are different, it's like integrating the triangle, and this is that triangle. Now this is a well-known quantity. This is the Hamming distance between omega and v. The first term is just the Hamming distance, how many different points. The second term is a constant, which we will call a square. Just some constant. It's the integral of phi square of x, and a square can be computed. Turns out that a square is actually L square h to the phi by 48. It's like integrating this guy from 0 to h, the square of this guy, so you can do that. We won't do it. Okay, so what we get basically is alpha. We have computed alpha. Alpha is the minimum over omega not equal to v square root, because this was a distance square, between omega and v times a. And a was this quantity. So a here is some square root of L square h to the phi by 48. And we will write this as just some constant c1 times h to the phi by 2, where c1 is the remaining terms. So the point is alpha is the minimum over omega not equal to v times the square root of the Hamming distance between omega and v times some constant times h to the phi by 2. So the issue here is that this distance can be as small as 1, because omega and v are two binary vectors, and if we selected them arbitrarily, they can just differ in one coordinate. And that is not good, because then it will make the distance too small and we won't get the right trade-off with the relative entropy. So you can easily prune out some of the vectors and keep the distance to be very large. This is like all vectors in this sort of binary cube, right? Every sort of vertex becomes 1 and the edge length is 1. You can just prune out a subset of vectors and get larger distance. And that comes from a theorem in coding theory called Gilbert-Warshaw bound. So what this says is that so it basically says that there exists a sequence of binary vectors of length t where the number is exponential in t, but the pairwise distance increases linearly in t. It's not small. We can select binary vectors that are sufficiently far apart and a large number of them, which is what we want. Okay? So the formal statement, or at least the way the form we want it is, consider omega, which is the set of binary sequences then for t greater than or equal to 8, there exists an omega, there exists a set, a collection of these sequences such that the size of omega is greater than 2 to the t by 8, and the Hamming distance between omega and v is greater than t by 8 for any omega and v in the set omega. So you have a collection of binary vectors of length t such that the total number of sequences, the size of this set, which is the n that we want, right? The n is increasing exponentially in t. It increases as 2 to the t by 8. So you have a lot of sequences still. Okay? However, if you look at the pairwise distance between any two sequences in this set, it is also going to be large. The distance increases linearly in the length t. So it's at least t by 8. This means you have a lot of sequences that have good mutual distance from each other. Again, these constants may not be the best ones. You can refine them and so on. But this is one version that we can use. So what this is saying is you can actually find, set t to be 20. Then you can find binary sequences of length 20, sufficiently many of them, such that the pairwise distance between each of them increases linearly in t, which is 20. So this is an existential proof. We won't prove this. The proof requires, again, some special arguments. I think it's a probabilistic method and so on. So that's not, what is important is that we should not take all 2 to the t combinations. We should select this omega and v from the Gilbert-Warshauer construction. This means that now dh of omega and v is going to be greater than t over 8 for all omega not equal to v. T is 1 over h, so this is 1 over 8h. And so what we get as a result of this is that alpha is the minimum of omega not equal to v square root of dh of omega v times c h to the phi by 2. This thing again is 1 over 8h. So alpha is greater than some c1, some constant. You have square root of h here and h to the phi by 2. So you have h squared. So alpha is lower bounded by some constant times h squared. Okay. Now, in a similar way, you can show that the relative entropy with a similar kind of calculation, which I don't have time, but you can show that the relative entropy between scales as dh of p and omega L square h to the phi over 96. It's again the same calculation that we did for in the Lee-Camp's method. So you have omega and v will define m omega and mv. You take the distance between Gaussians and you can show this. And this thing is upper bounded by t, which is 1 over h. So after a fair bit of work, what you get is that beta can scale as some constant times h to the 4. We're almost done, I think. So I'm not going to do the calculation for beta for you. It's just a calculation of the relative entropy between omega and v. We did it in the Lee-Camp's method. You have to repeat it here for slightly different functions. Again, you use the distance between two Gaussians, simplify things, and at the end of the day, you will get that beta is k times h to the 4. Okay. And then we want to set this to be log n by 4n, log capital N by 4n. Now n is like t to the, so n here is like 2 to the t by 8. So this is going to scale as 1 over 32 hn, right? So from, if you do all these calculations, you get that h to the 5 should scale as c over n, and so h is c over n to the 1/5. And when you put that back in alpha, so alpha is this, Rn of p is greater than alpha by 4, so what you end up getting is do the calculation, yeah, h square, so alpha scales as h square, so this is 1 over n, so this scales basically as some c prime times 1 over n to the 2/5, which is the scaling law you will get in this, which turns out to be the right one. So again, the idea is that you have to carefully select these functions, use them to decide the compute beta, the relative entropy, put it in the right form, and then plug that in and to get the alpha value. So this is how much I will talk about minimax risk. So we'll write the exam next week. None of this material is not on the exam. For those who came in late, the exam material is basically, where did it go? Is here I discussed, so if you came in late, make sure you note this. And after the exam, we will start with neural networks. Discuss some properties of neural networks. Okay, so this is the end of today's lecture. Sorry for going over.